Thank you for that kind introduction, and good afternoon to everybody. So I'm going to start with a question, help everybody wake up. So raise your hand if you've seen the movie Oppenheimer. Okay, good. Everybody's still awake, haven't put you to sleep yet. It's a good track record for physics. So as a physics professor who grew up in Albuquerque, New Mexico, I knew the facts of that story very well before the movie came out. But if you remember the first 15 minutes, that's the part that really stuck with me, because I think the movie makers did really a great job of capturing the excitement and the power and the wonder of this quantum revolution that happened at the turn of the century. And so I'm suggestively titling that Quantum 1.0 on my slide here. At root, what the advance was understanding the rules by which electrons, protons, and neutrons come together to make atoms. So a little later in the movie, quite dramatically, we also learned how to take those atoms apart to harness nuclear energy and make nuclear explosions. But as dramatic as that is, that's actually understating the impact of that revolution. I don't think it's a stretch to say that revolution underlies all of modern science and technology. So today, we're in the midst of a second quantum revolution, which people call Quantum 2.0. And so the distinction here is, rather than sort of nuclear power or bombs or anything like that, it's focused on information. And here, I use information in the sense of information technology. So IT, as we know, includes computers, networks, and the sensors that connect those computers and networks to the outside world. So that's pre-Quantum 2.0. So what is the new thing that we're bringing? Well, it sort of harkens back to what I said a moment ago. You know, how do electrons and atoms behave in a quantum mechanical sense? And that might sound pretty exotic and niche, but keep in mind, I am a physics professor. And so when I say electrons and atoms, I mean everything. I mean everything from the machinery of life. So here you can see an image measuring a single strand of DNA. The electronics in our phones and laptops, the avionics that keep airplanes landing mostly right side up. Chemical processes underlying manufacturing, petroleum, refining, the batteries that were mentioned earlier. So potentially the scope of impact for this advance in sensing and quantum sensing is really quite dramatic. So in order to understand where some of this power is coming from, let me introduce a metaphor of sort of learning Spanish in high school versus being a native speaker. So Quantum 1.0 is sort of the high school Spanish version of science, where we're thinking in classical mechanics, but studying quantum systems. Ultimately, our measurements are still going to be classical, and a lot of the ways we're thinking about the systems still originate in a classical paradigm. In Quantum 2.0, we're sort of cracking the code in how to think about quantum in its native language. Think quantum to speak quantum, and really use quantum systems to measure quantum systems. So extending that metaphor, high school Spanish is great. It lets you find a restroom. It lets you order a pizza. You can do a lot with high school Spanish, not knocking it. But if you want to pursue more subtle pursuits, like, for example, discuss with your friends the artistic merits of Barbie versus Oppenheimer, being a native speaker is really required to get that level of nuance. So now I've sort of diverged pretty far from physics. I didn't bet you weren't expecting to get that. So bringing it back into sort of the topic of quantum sensing, this has impacts on everything from drug discovery to materials characterization for microelectronics. And I'm going to talk a little bit more about a flagship effort being led here out of OSU in developing atomic scale quantum sensors. So this is a beautiful Blender image that one of my graduate students put together. That's the easy way to get to the atomic scale. You can see there's some atoms, some molecules, some other things here. What I'd like to do is tell you a little bit about how we went about going from this cartoon to realizing this in our lab. And that basically harnessed two convergent breakthroughs in chemistry and physics. So to discuss the first, I want to start off just with length scale. So this is an electron microscopy. Scientists in the audience may have seen this trick before. This is a human hair. The white bar is 10 microns. So for those not used to thinking in metric, that's about 1/1000th of an inch. If we go 1,000 times smaller, our scale bar is now 10 nanometers. And this is a cross-sectional image of an electronic device called a transistor. So the device extends out of the plane. And This is the electronic device that basically makes up the ones and zeros in digital computing and sort of modern computing. And you can see that we're at a level of technology today where we can put thousands of those across the width of a human hair, right? And that's the baseline. That's where we're getting started. So for quantum sensing and quantum information, we want to push even further to the atomic scale. So now this is a different flavor of microscopy called scanning tunneling microscopy, and this is an image taken in my collaborator Jay Gupta's lab here at Ohio State. And the first thing to point out is those bumps are not noise. Those are individual atoms. And the yellow atom in the middle, and the yellow island in the middle is a molecule that we want to use as a quantum sensor. So this is the first breakthrough, which is sort of driven by chemistry and atomic scale control of systems, and we want to harness that control for building our quantum sensor. The second breakthrough is in the development of a class of materials known as two-dimensional or 2D materials. So I'm going to warn you, I'm going to tell you how we make these, and you're not going to believe me, but here's my reference. The way this works is you take a piece of tape, and on one end of that piece of tape, you put an everyday material like graphite, the material in a mechanical pencil. You then fold the tape over, so you're sticking to both sides, and you peel it apart. The graphite fractures. You do that many, many times. Even better, you get a graduate student or an undergraduate to do that many, many times. And eventually that repeated fracturing process cleaves down to a layer that's a single atomic layer thick. So that's what you can see in the image there is a single atomic sheet of carbon organized in a hexagonal pattern. So there's many things one can do with this breakthrough. What our group is focused on is realizing that then we can use multiple different 2D materials and shuffle them like a deck of cards and deal out an electronic device at the atomic length scale that has the properties that we want. So this image indicates what our quantum sensor looks like. So the blue planes are these individual sheets of carbon or graphene, so multi-layer graphene. The green sheets are two-dimensional sheets of a related material, hexagonal boron nitride. So graphene or multi-layer graphene is a conductor, HBN is an insulator, so we've now made a metal insulator device called a tunnel junction. And nestled deep in the protective insulating layer of HBN, we can insert the molecular qubits that I showed previously. The cartoon you can see here is sort of the sketch of what that real molecule I showed on the previous slide looks like. So bringing these two things together, we can design our qubit at the atomic level and encapsulate it in a stack of 2D materials that allows us to address and read out that quantum sensor and then bring it to within a few nanometers of whatever we want to measure, whether that's a biomolecule, a battery, or a piece of microelectronics. So to close, I want to say something cheesy but true about how we really are building the future here at Ohio State. And I really want to emphasize the critical role of the academic research enterprise here. So it's the academic environment that allows us to take big swings and has really a research university like Ohio State is the only place in the world with a disciplinary breadth to be able to realize multiple breakthroughs in different areas, bring them together, and apply them to a given new technology to generate the breakthroughs and the impact that affect our economy and our society. So thank you.